trig. So if we're looking at our proofs, we're going to do 1 and 2 in this video here. So the first one we're going to prove is probably one of the most commonly used identities in trig, which is cos squared plus sine squared theta is equal to 1. And the second one we're going to do is the sine rule. And we're going to do two different cases for the sine rule, the acute case and the obtuse case. So to prove cos squared theta plus sine squared theta equals 1, we're going to start with a construction. And the construction we're going to do is the unit circle, where the unit circle is a circle with center 0, 0 and radius of 1. Once we have done that, what we're going to do is draw a point on our unit circle. It doesn't matter where it is. We're going to draw it in the first quadrant. And we're going to mark in the radius. I'm going to mark that as 1. And then we're going to see what our x and our y coordinates are by drawing a right angle triangle. In other words, we're going out on the x-axis and up on the y-axis. We're going to mark in the angle that is traced out by that point with respect to the x-axis. So in other words, this point here is out x and up y. And then our proof is fairly easy, because all we need to do is look at that right angle triangle and we say by Pythagoras, we know that h squared is equal to o squared plus a squared. And therefore we have the opposite, the adjacent, and the hypotenuse marked in on our right angle triangle. So that would be 1 squared is equal to y squared plus x squared. But we know that sine theta is the opposite, which is y, over the hypotenuse, which is 1, which means that the y coordinate is actually sine theta. We know that cos theta is the adjacent over the hypotenuse, which is x over 1. In other words, the x coordinate is cos theta, and that will always be the case. So therefore, we can say that y squared is sine theta to be squared plus x squared cos theta to be squared is equal to 1 squared. In other words, sine squared theta plus cos squared theta equals 1. And just as a point to note, if we look up here, that coordinate then can be written as x, in other words cos theta, sine theta. And if we look at page 13 in our maths tables, we will also notice that. If we look over here to the left, we can see cos A, sine A right there. So theorem 2 is where we're going to look at proving the sine rule. And the sine rule can be found on page 16 in our maths tables. And what we're asked to prove here is that A over sine A is equal to B over sine B, which is equal to C over sine C. Now sometimes in the leaving cert they'll just say prove that A over sine A equals B over sine B, which makes it just that last line unnecessary then in this proof. There can be two cases, the acute case and the obtuse case, and that's because sine is both positive in the first and the second quadrant, so we have to prove for both cases. So we're going to start with the acute case, and we're going to draw a triangle where all the angles in the triangle are acute. So we're going to label our sides. So we're going to have angle A, therefore the side opposite will be called side A. And I'm going to go angle B, and the side opposite would be B. And then of course you could have angle C, and the side opposite would be the side C. But I'm not going to put in C here, because what I'm going to do is we're going to divide this triangle into two right angle triangles. So you take your triangle and we divide it into 2. They're both right angle triangles. I'm going to call it triangle 1 and triangle 2, and I'm going to call this dividing line X. So in triangle 1, what we can say, if I do a little sketch there, this is X, this is B, and this is angle A. So that would be the opposite and the hypotenuse, and therefore the remaining side is the adjacent. And I know that sine theta is equal to the opposite over the hypotenuse. So therefore that means that sine A is equal to X over B, and therefore I can say that X is equal to B sine A. I'm going to call that 1. If I do the same then for triangle 2, again just break it up, we have angle B, A, X, right angle. So again I have opposite, hypotenuse, adjacent, and again sine theta is equal to the opposite over the hypotenuse. So therefore I can say sine B is equal to X over A. Therefore X must equal A sine B. But if both of those sides are X, then by equating 1 and 2, well, what that gives me is that B sine A is equal to A sine B. And if I divide across by sine A sine B, well, what that gives me is B sine A divided by sine A sine B is equal to A sine B divided by sine A sine B. On the left I can see sine A goes into sine A once, and on the right I can see sine B goes into sine B once. And therefore that leaves me with B over sine B is equal to A over sine A. So if that's all they asked for in the exam, you would be finished. But this one here is asking us to show that it's also equal to sine C. But of course I could have taken that original triangle and I could have divided it this way into 2 right angle triangles, which would be AC, angle C, and angle A. And we would therefore say, similarly, C over sine C equals B over sine B, or A over sine A. And again, you don't need to actually do out the full proof for that. And therefore we say, hence, A over sine A, A over sine A, sorry. It doesn't want to do my A there. Okay, just let me try that again. A over sine A is equal to B over sine B. I can't scroll down the page any further. Is equal to C over sine C. Okay, and then if we have to do the obtuse case, well, we have to draw an obtuse triangle. Like so. And therefore we would mark in angle A, side A, angle B, side B. And again, we need our right angle triangle from this. So what we're going to do is we're going to extend the base of the triangle out, drop a line down. And now what we have are 2 right angle triangles again. I call it new right angle side X. And if this is B and this is a straight line, then this angle here must be 180 minus B. So I'm going to have the whole triangle as triangle 1. And then the small triangle in here, that's been extended as triangle 2. So same again, we say in triangle 1, I do a little sketch. And therefore that's X, A, and B. So opposite, hypotenuse, the remaining side is adjacent. Sine theta is opposite over hypotenuse, and therefore we can say sine A is equal to x over b, and same as before, x is equal to b sine A. And then if we look at triangle 2, we have 180 minus b, a and x, opposite, hypotenuse and adjacent. So again, sine theta is sine 180 minus b is equal to opposite over hypotenuse, and therefore we say x is equal to x is equal to a times sine 180 minus b. But of course we know from our second quadrant that that's going to be the same value. In other words, sine 180 minus b is the same as sine b. So in other words, if I get sine 30, that's the same as saying sine 180 minus 30. In other words, sine 150 has the same value as sine 30. And now the rest of the proof is exactly the same as before. Let me just rub this bit out. Where we equate 1 and 2. And we can say a sine b equals b sine a, divide across by sine a sine b. And we get a sine b over sine a sine b is equal to b sine a over sine a sine b. And then we get our cancelling. So sine b goes into sine b once, sine a goes into sine a once, leaving us with a over sine a equals b over sine b. And similarly, c over sine c is equal to a over sine a. Hence, a over sine a equals b over sine b equals c over sine c. QED. Okay.